Now that we've had a chance to look at how an RSA encryption system gets set up, we're going to actually get down to doing some actual encrypting and decrypting in RSA. So the first thing we're going to do is we're going to set up some public and private keys for our RSA encryption. This is kind of a review from the last video. Then we're going to do a sample encryption and decryption. That'll be relatively straightforward. And then we're going to talk about some issues with encoding plain text and actually using RSA for that kind of plain text. In particular, encoding with things like ASCII. Alright, so let's go ahead and construct some keys. So first of all, we've got to pick our primes. And this time we're going to pick some 17 and 19. Those are perfectly good primes. They're two different primes, so that works. And that means our n is going to be 17 times 19, which is 323. So that's one of the keys that we're going to share. Next, we're going to compute phi of 323. We're going to do that privately. But since we know the prime factorization, we can do that. 17 minus 1 times 19 minus 1. And that gives us 288. And then we want to prime factor that because remember, we're going to eventually choose a number that is relatively prime with phi of 323. So we see we have factors of 2 and factors of 3 in there. We just have to avoid those as prime factors and we're good to go. So now when we pick E, remember we have to pick some number that's relatively prime with 288. We just have to avoid factors of 2 and 3 for primes, and 35 is a perfectly good number. That's 7 times 5. That's no factors of 2, no factors of 3. Next, we're going to compute D. Let's see. Now, D is a little bit tougher, right? We got to find the multiplicative inverse of 35 mod 288. Now, you could use the generalized Euclidean algorithm if you wanted to. Whichever method you use, you're going to end up with D equals 107. So our public keys are going to be E, which is 35, and N, which is 323. That's for the world to see so that anybody can encrypt. And so our private key that we're only going to share with ourselves, and I guess I'm sharing it with you on this video, is D equals 107, which we're going to use for decryption. All right, so let's see. I just want to work through this example so you can see that this actually does encrypt and decrypt the way you would expect it to. So if our plain text is 49, then our ciphertext is just going to be 49 to the 35 mod 323. Now that looks like a horrible computation to do, and I agree that it is. I'll show you how I did this later on in this slide. But when you do all the computations, you end up with 26. So that's going to be your ciphertext. Now I'm going to do the decryption on 26 to show you that you get back to the plain text. If we decrypt the ciphertext 26, then what you do is our plain text is going to be, now that one, our exponent is going to be 107, so you do 26 to the 107 mod 323, and if you do that computation, again, not by hand, please, that'll be very painful for you to do, you end up with 49, which is what you ended up with. Now, as you can see, when you get to even, I mean, these aren't even very big primes, right? These are like small two-digit primes that we were using, and already the computations look pretty horrendous. You can imagine that if we were doing 3-digit primes and 4-digit primes, and heaven forbid something like 100 digits in a prime, that's going to be extremely painful by hand. We got to find other ways. It turns out you can use wolframalpha.com for all these. That's one of the ones that you hopefully used in that last exam that you took. I will show you in class how to use that. It's extremely easy to use. Basically, you tell Wolfram Alpha what you want. It accepts what you want and spits out exactly what you need. So I'll show you how to do that in class. Anyway, so I do want to, before I let you work on some examples, because one of the examples you're going to do is actually take not just a number and encrypting and decrypting, but actually encrypting and actual characters. Now, encoding plain text messages is going to actually be a real pain in a practical manner, because if we encode a character in ASCII, each character needs 7 bits. And if you think about what that means in terms of how big your number n has to be, well, 7 bits is 128 possible numbers in base 2, right? And so that means your n has to be at least that big. Remember, our n was like a little bit north of 3 300, right? So 128, that's just one character, right? We had 323 in the above example that we did. And if we think about how many bits that's able to encrypt, well, 7 bits got up to 128. 8 bits is what, 256? 9 bits is 512. 9 bits is already too big, so we can only encode 8 bits with that, right? We barely more than like a single character. So that's kind of troublesome in terms of that. So when that's going to really affect us when we choose the primes that we need to make our N, our public key. So I'm just going to talk about some of the issues in choosing those primes. So our main issue, of course, is security. We want to make P and Q big enough to make it so that if somebody wants to try to factor N to try to break our cipher, their life is going to be difficult. But also we want to make P and Q big enough so that we can actually encode the plain text. So when we multiply P and Q, we get a number big enough to encompass all the possible ways that we can encode our text. So if our plain text is of length k, so in other words we have length k characters in our plain text, we need to make sure that not k characters but k bits, we need at least 2 to the k, and to be at least 2 to the k. And that can be a very, very big number, especially if we have a long message. Remember, the long message, we're going to multiply that message by either 7 or 8, depending on how many bits we use to encode our characters. Of course, if you don't like that, which I'm not a big fan, right? You can actually encode the plain text in blocks. So let's say your N is only big enough that you can encode 10 bits. Well, you may have 1,000 bits in your message, but what you can do is you can break up that message into groups of 10, right? Encrypt each of those blocks individually using RSA, and then sending that along as your ciphertext. You just have to make sure that your recipient knows how long the blocks are, so that they know how to break up the ciphertext to decrypt it. And remember, we did something very similar to this in SDES. Remember, SDES encrypted and decrypted in blocks. We did it in 12 character blocks, but in the other simplified one, they did it in 8-bit blocks. All right, so now I think you're ready to work on the activities for RSA encryption and decryption. You're going to have a lot of computation to do, and I'll make sure to teach you how to use Wolfram Alpha so that you can do those computations.